Hello and welcome to Build Your Own CPU Part 14. In this episode I'll be covering the CPU simulator I wrote in BASIC and also the assembler, because hand assembling the noughts and crosses program would have been quite a big task, so I wrote a program specifically for that. Let's start with the CPU simulator. And on the screen here I've got the simulator running on the right hand side here, and on the left I've got the actual basic program that runs it. This was written in a programming language called Just Basic. It's a freebie and quite simple, but it does everything I need to do. Now if we start at the beginning, right, this is for personal non-commercial use again. If you want to sell anything, you've got to contact me first. Starting off, we'll define the variables. So all the variable names here, you know, start with the letter C. It's a capital C. Now in Just Basic, uppercase and lowercase are important, and there are some reserved words. By just putting a letter at the beginning, it stops these clashing with any reserved words. It makes it a little bit more difficult to read. I can't remember why I chose the letter C, but that's the way it is. And then we've got some more variables. These are all the T states, the instructions, and the source and destination modes. You may notice that these variables up here, like add, sub, A output enable, A input enable, they're all the control signals. So I just named them the same to make it easier to understand. Now the purpose of this was I worked out all the logic that I'd needed to do all the instruction decoding, and then I had to test it, and I thought, well, if I build the hardware and something's wrong, it's a lot of work. So I thought I'd write a simulator, and I'll make the simulator work exactly as the logic diagram I designed was, and then run it through here, run all 112 instructions through here, and see if they did exactly what they should do. And if they did, then I'd then build the hardware the same. Unfortunately, when building the hardware, thought, oh, I can change this bit here and that bit there to save a few gates, but then didn't come back here to test it, and that's why there was some mistakes. I had to put in a couple of OR gates. If I'd followed what I programmed in here exactly, it all would have worked first time. Define some IO and memory, etc. Just arrays. This is just the graphics on the screen with what they're called. And the little boxes, these tick boxes here. They're not for us to tick. It turns them on and off to let you know what's going on. And just reset the variables. For some reason, register 2 set to 200. Doesn't really matter. Alright, the first thing I do is update the screen and then set the T state to 0. Run this decode program. Decode, subroutine decode, is actually all the ands and ors that do the instruction decoding. Then update the screen again. Now we get down to the main bit of it. This I can make run auto, so it just steps through automatically, or I can step it half a step at a time manually. That clock speed number there, that just defines how fast it runs if you've got it running automatically. We've got a timer that just waits for that period of time. I think that's in milliseconds. And then here's where we start here. If the clock is set to 1, then go to the clear bit down here. If not, it's at 0, which it will be the first time come through. Sets it to 1. Make sure this is it's like a clock going tick, 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 but this is for setting the T states. Here, sort T clocks actually sets the T states. Then it does a decode, as you run through all the ands and ors. And then after that, if there's any outputs coming from any of the registers, it actually puts them onto the internal data bus, and then does update the screen again. And then it comes through here, waits that period of time again, the 200 milliseconds I think it is. And then it does the pulse. So strobe on is basically turning the pulse on and pulse off. And part of that is that subroutine, it will actually latch any data into any registers that have got their input enable turned on. Then it updates the clock again, sorts out what the T signal should be doing to T state. Run the decoder again. You can run the decoder as many times as you like. You can call it and call it and call it. It's just when you've got lots of ANDs and OR gates, they're all running parallel, whereas writing software here, they run sequentially. So you've got to be careful that a early if statement doesn't rely on an output from a later if statement. But I've put these all in the correct order, so that shouldn't happen. But if I hadn't, I could have just run that several times and it would have sorted that out. I believe that's how I ran the first initial version of this. I've tidied it up a bit since then. And update the screen again. And that just loops around and around, going through all the T-states of 0 to 15. So, let's scroll down a bit. Well, let's run something through it first. I originally had this where I'd put values into registers and run it, but I put a button there where you can actually load in the assembly code. So, under here, this is the actual noughts and crosses program. I'll go through this in another video. But this is the assembler for the CPU. As you may remember, the first command is out RAM address 240 with 0, set the ROM page. And then the next instruction will be your code, wherever you want. So this is moving what was in RAM into the ROM page, and that's the same on every page that goes through. And at the end, this is where you'd change it. So here it's move the page number you want into that value, then branch back to here, and that sets your page. So you're on a different page. But I'll say we'll go through this later. And I've got this here so I can show you some special functions that happen within it for the assembler. Right, so if we load in the actual, this is the final assembled code. It's not this source code, it's actual binary code. So we load that in, and everything's set to 0, apart from that register for some reason. So program memory is putting in at 0, which is got the number 144 in there, 240, 0. So if we step this on, clock step, we'll step that on. So we're now on T0. So we've got A input enable on. So we put in the program counter, it's output enable. So the program counter is on the internal data bus going into the A register. It's also going into the memory address register. That's always T0. So if we bring up, you can see this is the T0, A input enable, program counter output enable, memory address input enable. There's those 3 bits there. See, they're on there. We go to the next step, which is everything's off again. You can't really see it here, but the program counter has been put into the memory address register and the A register. And we go to T1 is on, with lots of bits on. So we pop back to where we were on here. T1, adder, output enable, program counter input enable, and all these for reading from memory. So it's 1, 2, 3, 4, 5, 6, 7 different signals. 1, 2, 3, 4, 5, 6, 7, 8. What is that? Oh, it's C set there. That's the same one. I've got it on here twice. So you can see what's going on here, but you also want to see what's going on over here as well. So I've put it in there twice. So that's a T1 and it's off, so everything got stepped through. And what's happened is the address 0 had 144 in it. This has moved on there. Program counter's moved on to 1. That's now the program counter plus 1. But it had 144 in there, which has gone into the instruction register. So there's 144 in there, which is the instruction out with a source of memory and a destination of memory. Which, if we look on here, there we go, out, a memory address, and another memory address. For the in and out instructions, I'll put a square bracket there instead of a round one. The assembler doesn't care, and that just differentiates between memory and I/O. So if we pop back to here, that's now T2 is just done, so we click on again. Oh, sorry, that was T1. Now we're on T2, which is starting to perform the instruction, which is T2 here. So we have A output enable, program counter output enable, memory address register input enable. So we go through this step now. If we pop back to there, It's a T2 state. So you can keep stepping through these, and you can see all control signals going on and off. Now, this is all based on my theory of how it should work. And so you run all the possible instructions through here, and it will pulse through them all. You can see the right things come on and off. Because this box here is if you're doing this in using say a ROM or EEPROM for simulating your instruction decoder, then these are the actual bits you'd have set within your EEPROM. And this would be the separate addresses that you'd step through to do all 13 steps. But we're doing it with logic instead. So if I put that onto clock auto, you'll see it will step through, and that will be the CPU running. So if I actually run this on the CPU itself, when you look at it, all those lights you see flashing, all these signals going on and off, plus some others. So that completely simulates it, goes through every instruction, and what will happen is this will end up getting in a loop, going round and round, because the actual code, after it's done a few setups here, sits here scanning the keyboard, going round and round. So that's the CPU simulator actually running. The only thing it can't do is I can't actually put inputs into it. So, but it was only written to test that what the instructions do to actually send the correct signals out. And we'll leave that going for a minute. And if we go back to the actual code, here, we are going around this loop here and running these instructions. So if we go through some of these different instructions, what it's doing, so sort T clock, so turns all the T's off to start with, so they're all off. If this CLK variable is set to 1, then it sets the T state. If it's set to 0, it'll turn it off. That's just so that on the second loop you go to the T of nothing on there, and then register output into data. So as I said earlier, if when you've got your clock turns on, he's going to start putting data onto the data bus, and this goes through to see which bits are on, and if they're on, he puts that data onto the internal data bus. So that's called data int. So only one of these should actually put data out, but it just scans the whole lot. And we've got strobe on. This is the pulse, when the pulse comes on and goes off. So if we turn the pulse on, it then checks to see what's where, and if you've got, say, like A input enable is on, then the A register will have put into it what's on the internal data bus. Now, more than one of these can go on at once, because at the right beginning we have the A input enable on and the memory address input enable on, so they both get the data put into them, which will happen on every T0 state and some others. And update the screen, that just makes it write things to the screen. Call F7, update what's on the screen here, the tick boxes and the numbers. Here is where we are actually demultiplexing the instruction. So we have to do an AND, then shift it. We only want the top nibble for the instruction, and then that's the instruction number, and then it just turns this variable on or off, depending which instruction it is. So only one of these will ever be on at any one time. And then you're going to do the source address and destination address. This is basically what those demultiplexer cards do, so it's sort of testing those out as well. It's sort of, and that's only 3 destinations put in there. And then this is the bit that actually does the work, the decode. So the first thing you do is demultiplex everything to get all your instructions there and all your source and destination set. It then does, right, if we're on T0, now if we look at the logic that I've done, we've got, yeah, so on T0, we'll be going out to those 3 outputs, which is the same as this, T0 there. Then there we go, if T0 is 1, then A input enable is on, program count output enable is on, the memory address register is 1. If not, then there's 0. So I've got a T0 on there to let you know it's to do with the T0 state. Because what we're going to do is come near the end, there'll be a load of OR gates. And all the ones with A input enable on will all be ORed together, and program counter output enables will be ORed together. We'll see that shortly. So we've got T1. So if T1 is on, turn all these values on. So we've got the same names here. I've tried to keep the names the same all the way through. So all these variables get turned on. So T1, turn all those on. If it's not a T1, then turn them off. Now T2 starts to get a little bit more complicated. So we go back to T2. We've got some ORs and some ANDs, etc. So if we've got source 0 or 3 and T2, then turn those 3 on. If we've got source 0 or source 3, either of those, and it's a T2, then turn those 3 on or turn them off. If it's a T3, do those. There we go, T4, which is the same as T4 there, those 4, and then T5 is just those 2. We go back, T4, there's T5, just those. And then we'll do 8, 9, 10, 11 as well, which is almost exactly the same code, except it's the destination this time instead of the source. And then we come down to T6, which is a bit more complicated. And we've got T6 on here. There you go. That's what's on the T6 card. So T6 is on, then turn B input enable on. So rule A, T6 is 1, then turn B input enable on. That's the T6 rule A. The reason is here, I can't just use T6 because it would be elsewhere as well. I have to say it's rule A and then rule B. So that's rule A. This will be rule B. This will be rule C. Well, that'd be rule C. This will be rule D, E, F, G. Which you may remember from the T14 cards, it's T14A, B, C, D, and then the second card is T14F, G, H, etc. So I'll split them all into subsections. I actually got all the different C's. So that one's, he's looking for it to be a 0, setting it as a 0 or 1 in the opposite way round because it's a NOR gate. Then we come down to T12, all similar sorts of stuff. Now I could do all of this in one chunk, but I've tried to make this exactly the same as what's actually on the logic gate drawings, these logic gate drawings. So I'll do this bit and then I'll have a signal here that feeds onto that one, and then a signal here that feeds onto this one to try and make it authentic and exactly the same. So we know it's a genuine test. We're all down there, and then we go to T14 at the end here. This one's a bit more complicated, and we end up with some intermediate values. So you've got like T14RA2, that may be used in one of these others further down here. Let's see if we can find one. 9, T12, T14. So this one here, this value here that goes out here, that's T14A. It's also used here as well. So I'll have a variable that denotes what that is, and I'll use it here rather than doing all this again. So T14, if 13 is 1 and 14 is 1, then rule A1 is off. There we go, rule 1 is off. And then rule A2, there we go, rule A1 and rule A2. And then A, rule A1 is on, and rule A14, A2 is on, and T14-1 is on, then rule A0 input enable is on. Sounds a bit complicated, but that's all this. So if that's rule A1, that's rule A2, they're on, and T14 is on, then that one is turned on. I've got several if statements doing the one logic stream. So each if statement will be a gate. It will be a NOR gate or an AND gate or an OR gate. Then you've got rule B and all of them. So come down to rule F, that'll be on the next card, physical card. And it just laid out exactly the same. Now once you've done all the ANDs and ORs, you've then got to join them together. So all these signals here all have to be ORed together, as we saw on the OR gates. So all these signals are going out into the big bus, the matrix, and then this is the matrix being picked off into the OR gates. And this is simulated here. So A out enable, what things have got A out enable on? Well, there's T5 A output enable, and there's a T11 A output enable. So if either of those are on, or so it's that one or that one, then A output enable is on, if not is off. So there's your first OR gate for your A output enable. A input enable, well, you've got one of those from T0, we've got one from T2, we've got one from T4. So if any of them are on, then turn it on, otherwise turn it off, and so forth through the others. So these are just all the OR gates that are on those three cards with all the OR gates on. So it does exactly the same, and then when it's finished, that will just return from that subroutine to say it's done all the logic exactly as it is built in hardware. And these bits of code here, that's just to make sure the screen updates. I mean, if it's been set on, then update the screen. If it's been turned off, then update the screen. So it turns the ticks on and off. This is all just basics stuff. There we go, all the way down. There's loads and loads and loads of each checkbox. And that's just a bit where we load the memory up with the program we want to run. Let's pop back to the program and see what's going on with it, shall we? What screen are we on? We're on that one there. Here we go. Oh, look, we've got program step 30. Oh, it's gone back to 23, 24, 25. Stepping through, program counter stepping up. If we look at the actual code, that will be this loop here, going round and around that loop. I can't make it step on because I can't actually put a value in. Because what I did is I didn't create it to run this program. I created it to test the instructions. So I can only put the individual instructions in. I wrote a test assembly that just had all 112 instructions in, and it just went through them one at a time. That's all I need to do with it. So it's not a whole simulator, it's just simulating the instruction decoding side of things. And let me see how the data's flowing through. Now here we have the assembler. Writing the actual code, we look at the actual code for noughts and crosses here. There is no branch relative, they're all absolute addresses. So when you come to a branch like this instruction here, scan go is an actual address. Well, that's just there. Scan again is an actual address, so up there. So that will be, I think it's 24, so this will say branch to 24. But if I was to change the code in the middle of here, then these addresses would all be wrong and I'd have to recalculate them all. And that would have been very difficult to do and prone to lots of errors and bugs. So I decided to write an assembler that will use labels and adjust them whenever I've reassembled the code I'd written. So here's the assembler. Personal, non-commercial use. Let's create some global variables. All the dimensioned arrays are all global as well. So I just picked 10,000. Well, that one's only got 1,000 on that label. So you can have up to 1,000 labels, but you can increase these to whatever you want. This first one's all to do with selecting files. It's a two-pass assembler. So we create a window. So let's bring the window up so we can see it. That one there. Oh, it gets in the way a bit. So there's lots of different windows in here. If we run down, we've got button clicks, and what we'll do to start with is we've got a read-in assembler. Refresh the screen, convert everything to capital letters to make things easier. Remove any tabs I've put in there. Remove any comments. And then the cut lines means to set the right sizes. You've got to chop it into an instruction and then the two possible arguments that go with it. Refresh the screen again. Then use your pass 1 and 2 for doing it. So pass 1 will calculate the values of where the labels are. It does some of the assembling, but works out the address of the labels. And then it will go through and do, on the second pass, it'll actually put the values of the labels in the right places for, say, the branches. So you see down here it says branch to start. Well, start's got a value and it'll have to put that in there. And then once it's done all that, and it's got the assembled program, it then disassembles it and displays it. This is just to check that things have gone right, because this assembler's only got a few basic bits of error correcting on it. You have to be careful what you type in. Since I wrote it, I mostly knew what I was doing, and so there wasn't too many errors, and I didn't have to write too much. So it then writes the binary file automatically out to a file. It just changes the extension, and it will do two of them. It will do a binary file, but it will also do one that's for cutting and pasting into the microcontroller assembly listing, because you have to define the actual bytes that are in the simulated ROM. So it creates that as well. And it's basically just a load of subroutines, and they're called in that order. If we actually run it, should we load in an assembly? So we load in the noughts and crosses one. So if we load in the actual noughts and crosses, so that's the latest version, 76, it will create this file and this file. This one's the actual binary, so if you're using a ROM chip or an EEPROM, that's the file you would burn. If you're using a simulator in a PIC chip, you'd use this file here, because that's a source file that's used in the microchip. So let's just get the assembly first of all. Open that one, which is this program here. And it's loaded it in. There's the actual, each line, it's chopped each line up, well, individually lined, and turned them all into capitals if you'd use lowercase. See, I've written in lowercase here, they're all capitals up here. And then it runs down to try and find the instructions, chops them out, first parameter, here, second parameter. And this is the actual code that it's generating for each one. So we'll have 144 will be, that's the out command, it's 144. This 240 here is we're moving out. The next byte would have been 240, and one after that would be 0. So there we go. Memory address 2 would be a 0. Then 29 is move, 0 into R1. 20 is a move as well. It's different type of move. It's moving R1 into 241, and that repeats down. So this is the actual hex of it all. Now, in here, there's some special instructions in the assembler. So there's one here called page 0. That tells the assembler that we're the first 256 bytes, because remember it's all in pages. So we're on the very first page. And at the beginning of each page, in the noughts and crosses program, we always do that instruction, which is set the page. And then we run to whatever we want. Now that, between page 0 and page 1, is not 256 bytes. It's just ended there. And as the assembler comes down, it will see page 1. So it'll know, well, I've got to jump forwards to address number 256, which is page 1. Because the CPU doesn't actually understand that, but it's going to chop them all into pieces. And this bit in between here, it will pad out with zeros for the EEPROM. So as we come down here, it calls it a NOP. There isn't really a NOP instruction, but it's good enough. And as we keep scrolling down, there we go. There's page 1. I wish I could get all these synchronized together. I'm not sure how to do it, but this is like the labels. It searches for labels. So here's all the labels that you're going to be branching to in places. And these are the values that it's created for those labels. So scan go is at 30, scan again is at 23. You may remember when we had the simulator running, it kept going between 23 and 30 because that's where it was scanning around. And so these are all the labels and what value they got. Then it does a disassembly of it and creates all this over here. So this over here should match what we've got over here. This is sort of just a little check for us. Page 0 address 0 and absolute total address of 0 has got the command out 240 to 0. And then page 0 address 0, absolute address 3 is that. So that instruction is the same as that one. So this is just a check. Now if we scroll down to page 1, so here look, you see we've got all these knots. We go down to page 1. Where is it? There we go. So page 1 address 0. So this first one is the CPU address, what the CPU sees, but it's actually ROM address 256. And then we've got those commands for page 2. I believe there's 7 pages in here. Go down, yep, page 7. So these are all the program for the noughts and crosses, and that's just the padding in between. We can actually look at that if we go and find the file, because this now will have created a load of files. If I quickly open this here. So if we look in the actual noughts and crosses program, there's the source that we just assembled, and here's the new assembly of it. So there's the binary. If we look at the actual binary, bring the binary over, here's the actual code that will be put into the ROM chip. Page 0, page 1, page 2, page 3. So that's if you're going to do a ROM chip. If not, you've got this one with the, you're going to use the simulated ROM. This here is what actually gets cut and pasted into the assembler for the microchip. So here we have the assembler for the microcontroller, and this is where we simulate the ROM, and that's all the bits in there. So we have just actually taken that. This is that source file, and that's the actual code in it. So I just cut and paste that straight into here. You can see it's the same code, and that's all the ROM. So if ever I update the noughts and crosses program, I'll run it through the assembler. That creates this file, which I'll then cut and paste straight into the microcontroller source code, recompile that, reflash the BIOS that's got the ROM code in it, and away we go. You could play around with that and create your own program and put it in there and make it do something completely different. If you had say you're doing it with ROM chips, then you just have to use this file and flash that into your ROM instead. That's the assembler basically. If there are errors, it will pick them up here. Let's introduce an error and see if it'll pick it up. Right, where are we? Find the file. That one there. Let's put an error in it. Let's make that value too big. Save that. And let's run the assembler. Right, so if we run the assembler now, we've got to reload it in. So I'll just create a new one. That one there. We run that. Oh, look, it's found the error. Byte 1 has got an error on it. So if we find byte 1 on the very first byte, oh look, we've got an error here. -994 is actually the error code. So that byte is bad. So we can then look back at assembler and go, oh look, it's too big. And what about if we do, I'll delete that out there. That should be R2. Right, remember that's R2. Reload that in again. Run that. Yeah, you didn't pick that up. So it's not foolproof, as you can see. Where are we? That would be after the last move statement. The move. That should be out and then an in. Oh, look. Turned into a branch instead. It's got, oh, those are the into 213. Yeah, it's taken data there, thinking it's an instruction. So as you can see, it's not foolproof. Correct that. What I'll do is I have to do it again, otherwise my binary and source files will be wrong. Open that, run it again, because that overwrites them, and that's all running correct. So it's not 100% catch all the errors, so you have to be a little bit careful. So where's the actual code again? There's the actual code. So you may remember I was talking about you can jump to, at the beginning is always set the page, but you can branch to any page you like. So you're moving to page 1 now, or page 5. And each page I've got set to do a slightly different thing. Page 1 there. page 2, doing all things. I will go through this in the next instalment, otherwise it'll be too much. So you have an assembler and a simulator, all written in BASIC, so they're easy to follow. So there's the assembler. I've written in just a simple BASIC language. You can download for free if you want to modify it, make it better, put some more error correction in, etc. So that rounds it up for this episode. So in the next episode we'll go through the actual noughts and crosses program and the philosophy behind how that works. So don't forget to like and subscribe, and hopefully I'll see you in the next part.